Hello everybody, good morning. Myself Dr. Shubhankar Sen from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the third lecture of Module 7 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall begin with the differentiation of explicit and implicit schemes used for discretization of the marching problems. Then we shall illustrate a numerical problem in one dimension where we shall show computations using the explicit, implicit and the Crank-Nicolson schemes. So first we begin with the differences between the explicit and implicit schemes. Explicit schemes, implicit schemes. These explicit schemes, they are used only for marching problem. Used only for marching problems. Implicit schemes, they are used for marching as well as equilibrium problems. Used for marching as well as equilibrium or steady state boundary value problems. Explicit schemes are conditionally stable. Here, implicit schemes, they are unconditionally stable. For explicit scheme, there is clear restriction on the time step size. Restriction on the time step size. Optimum delta T is determined from stability criterion. For implicit schemes, theoretically, no limit on the time step size. However, large delta T does not ensure unconditional accuracy. For the explicit schemes, when we perform the mass lumping method, we can diagonalize the left-hand side mass matrix. The LHS mass matrix may be diagonalized, and in that case, matrix inversion is not required. In case of implicit formulations, the calculations are more involved than its explicit counterpart. We have to deal with the Ax equals to B equation where A is always non-diagonal. Now we illustrate the numerical solution of one transient heat conduction problem in one dimension subject to essential boundary condition. This problem we have already solved in the previous classes for the steady state problem or for the boundary value problem. Now, with the presence of the time derivative, this problem reduces to a marching problem belonging to the parabolic type of partial differential equation. So we shall solve this problem by using three methods. We shall illustrate the implementation of explicit scheme, implicit scheme, as well as the Crank-Nicolson scheme. The governing equation is del t equals to alpha del square t plus s tilde, where alpha equals to 1 meter square per second. It is given. Length of the rod is given as 1 meter. So here we draw the rod. This is x equals to 0. This is x equals to 1. This is the x-axis. We have temperature specified at the left boundary as 100 degrees centigrade. At the right boundary, it is 50 degrees centigrade. Our governing equation is del t equals to alpha del t to del xt plus s tilde, where s tilde equals to 1 watt per meter cube and alpha equals to 1 meter square per second. Now, we solve this problem by discretizing the domain using 5 finite elements. Let us discretize the domain. Mesh generation. So we make 5 finite elements. Element 1, element 2, element 3, element 4, element 5. Then our global node numbers are 1, 2, 3, 4, 5 and 6. So this is our mesh size. So mesh size delta x equals to 0.2 meter. So num np equals to 6, num l equals to 5, delta x equals to 0.2 meter. So this is a representative finite element. Local node 1, local node 2. This is x1e and this is x2e. This is the x direction. Now, when we find the weak form of this equation, we already shown in the previous class that the weak form leads to the following element level matrix equation system. The weak form reduces to the following matrix equation system. Me into dte dt at the element level plus the stiffness matrix Ke into Te equals to Fe. Now we generate the ID array. So here our 6 global nodes, they are identified first. For the first global node, the equation number is 0, and for the last global node, the equation number is also 0. Then for the remaining 4 nodes, our equation numbers are 1, 2, 3 and 4. So conventionally, for these 4 nodes, we should denote the unknowns as T1, T2, T3 and T4. For this particular problem, we designate these temperatures as T2, T3, T4 and T5. So T6 is given as 50 degrees centigrade and T1 is given as 100 degrees centigrade. So this is global equation numbers, and these are our DOFs. So now we generate our ID array A versus ID A. So we have 6 nodes, 1, 2, 3, 4, 5 and 6. So our equations are 0, 0, 1, 2, 3 and 4. The LM array, this is for the ID array. From the ID array, we can construct the LM array. So this is E, this is A, this is I, this is NEE. Elements 1, 2, 3, 4 and 5. Local nodes 1 and 2. So local equation numbers will be 1 and 2 when our IDOF is 1 per node. So then the global equation numbers, these we get as 0, 1, 1, 2, 2, 3, 3, 4 and then we have 4, 0. So I remind here again that the degrees of freedom, instead of designating them as T1, T2, T3 and T4, we have designated them as T2, T3, T4 and T5 at global nodes 2, 3, 4 and 5 respectively. For this particular strong form and for this particular two-noded bar element, we already know the expressions for KE, ME and FE. So here we consider the initial condition for this problem. So for all 4 temperatures, we take a 0 initial guess. We consider Tj at time equals to 0 for j equals to 2 to 5. This acts as the initial condition considered for the transient problem. So these 0 values, this represent a trivial initial condition which can be conveniently used for this particular problem. So now we have the element level stiffness matrix. We already know that Ke, this is equals to K by delta x minus K by delta x minus K by delta x and K by delta x. Our K is 1, delta x is 0.2, this is minus 1 by 0.2, this is minus 1 by 0.2 and this is also 1 by 0.2 along the diagonal. So this gives us 5 minus 5 minus 5, 5. This is a 2 by 2 matrix. So for this case, our S tilde equals to 1 watt per meter cube. So it means that we have source term present in our calculations. So we know that FIE equals to integration over omega E S tilde psi IE d omega E. For two-noded bar elements, we get FE equals to S tilde delta x by 2 delta x by 2. So this gives us S tilde is 1, delta x is 0.2, so this will be 0.1 for both the components. Then we go for the load vector. The assembled load vector, it is directly shown here. The assembled load vector was already computed in our previous classes. For this problem, as a steady state boundary value problem governed by elliptic PDEs. So I suggest the students to look into the previous lectures for one-dimensional steady-state heat conduction governed by the Poisson's equation by using two-noded bar elements. In that case, we have already constructed this assembled matrix, particularly in the lecture where we have compared the finite difference, finite volume and finite element solutions for this same problem subject to steady-state condition. So after implementation of the essential boundary condition, we get the load vector F0, which is constant with respect to time. This load vector, since the boundary conditions, these are independent of time, or these are time independent essential boundary conditions, this load vector, it does not change with time, so it remains constant. And similarly, here we have shown the assembly process. So assembly was already shown in conjunction with 1D Poisson equation solved by using finite difference method, finite volume method, as well as finite element method. So in that case, we get our capital K as a 4x4 matrix, K11, K12, K13, K14, K21, K22, K23, K24, K31, K32, K33, K34, K41, K42, K43 and K44. So this gives us a 4x4 symmetric, tridiagonal, positive, definite and banded matrix. So in one dimension, by using the Galerkin formulation, we always get a tridiagonal matrix with two noded bar elements. So this we are using the Galerkin finite element formulation. Galerkin finite element formulation. Now, putting the values of the element level entries, we find the global or assembled matrix as we have shown 10 minus 5 0 0 minus 5 10 minus 5 0 0 minus 5 10 minus 5 0 0 minus 5 10. This matrix we have already constructed. Now the mass matrix also assembled from the element level to generate the global mass matrix. In the first and second lectures of this 7th module, we have discussed the mass matrices of the two-noded bar elements. So for two-noded bar elements, the element level mass matrix is given by ME equals to delta x by 6, 2, 1, 1, 2. Our delta x equals to 0.2. This gives us ME equals to 0.2 by 6, 2, 1, 1, 2. This gives eventually ME equals to 0.2 by 3, 0.2 by 6, 0.2 by 6 and 0.2 by 3. Now 0.2 by 3, this is 2 by 30, so this will be 1 by 15. 1 by 15, here we have 2 by 60, so it is 1 by 30, 1 by 30, 1 by 15. So this is our element level mass matrix with entries 1 by 15, 1 by 30, 1 by 30, 1 by 15. Now we have performed the assembly of the element level mass matrices and we got a tridiagonal global mass matrix. So this is also tridiagonal global mass matrix and this is symmetric positive definite as well as diagonal dominant. Now for understanding of this assembly, we can just show the LM array once more. LM array used for assembly. This was E 1, 2, 3, 4, 5, A 1 and 2, I 1 at both the nodes, NEE 1 and 2 at local nodes 1 and 2. NEE is the number of equations per element. Now we had the equation numbers as 0, 1, 1, 2, 2, 3, 3, 4, 4, 0. So this is our mesh. So here the first node here T1 was 100 degrees centigrade. Here T2 is unknown, T3 is unknown, T4 is unknown, T5 is unknown, and finally at T6 we are given with 50 degrees centigrade temperature. The mass matrix M, stiffness matrix K and load vector F are constants and hence independent of time. Now we shall show the illustration of explicit method. For explicit method we shall use three different values of time step. We shall start with a high value of time step. We shall take delta t equals to 0.1. So our semi-discrete form was at the assembled level m dt plus kt equals to f at assembled level. Now let us consider n as the time step count. Then we can have m t at n plus 1 minus t at n divided by delta t plus k into t at n equals to f at nth level. From here we find mass matrix into unknown temperature at n plus 1th level equals to mass matrix into unknown temperature into known temperature plus delta t into the load vector which is known minus delta t into stiffness matrix into the known temperature. So this equation, it serves as our governing equation for performing our calculation. So temperature at n equals to 0 represents the initial condition that we have taken as T2, T3, T4, T5 at the 0 level, as all of them are 0. So we start our calculation with n equals to 0, and then with the delta t equals to 0.1. The first step calculation, delta t equals to 0.1. So in the left hand side we have the mass matrix M, then we have the temperature vector at the first level. So this is n plus 1. Now n was 0. So in the right hand side we have the mass matrix again. This is the initial guess or initial condition T0, plus this is our delta T, and this is our load vector from the boundary condition at source term at time level equals to 0, minus this is delta T, this is the global stiffness matrix, and this is the degree of freedom or temperature at the initial condition. So here T2, T3, T4 and T5 at time level 0, they are all equals to 0. So in the next step we show the calculation. So here all the known quantities we have shifted to the right hand side. So here we have, this is M, this is T, n plus 1 equals to M, this is T at 0, this is delta T, this is F at 0th level, this is delta T, this is the stiffness matrix K, and this is temperature vector at the 0th level for the degrees of freedom. By performing this simplification, the left hand side we get without mass lumping. So in our calculations, for the explicit calculations, we have not performed the mass lumping. It means that we have not diagonalized our mass matrix. So we have not performed mass lumping to diagonalize the assembled mass matrix. For each explicit calculation, we have inverted the assembled mass matrix. Then finally we are getting the matrix equation system AT equals to B. So this is equivalent to A, T equals to B, where T is the unknown temperature at the first time level. Performing this calculation, we get the solutions for temperature. So these temperatures, we can see that the first value and last value, they are quite high. Now these solutions, they will be used as initial condition for the second level of calculation. So when for n equals to 1 for the next time level, we shall get the temperatures at the second time level. Use these temperatures as initial condition for the n equals to 1 calculations as shown below. So here for n equals to 1, we get the temperatures at n plus 1th level. So we already have the generic equation. This is the mass matrix, this is the temperature at n plus 1th level. This is again the mass matrix. This is the temperature at the nth level or the first level. This is delta T. This is our F at the first time level. This does not change with time. This is again delta T. This is the stiffness matrix which is constant, and this is the temperature vector at the nth level or the first time level. So we perform this multiplication in the right hand side, and then we get, after calculation, the matrix equation system. It comes as this is AT and this becomes B, and then if you see that just at the second time level, the T2, T3, T4 and T5, these values are absurd. These values are too large. So here we can see that the vector solution just at the second calculation level, it is too large or unrealistic values. So these values we have obtained by using a high value of delta T of 0.1. So here, instead of showing further calculations, we have summarized our divergence of solutions for this case using delta T equals to 0.1. So we have shown up to 10 seconds results. Then you can see that in the y-axis or in the temperature axis, the temperature has reached at the level of 10 to the power 13. It means that these solutions are certainly diverging. Now the right hand side picture, it shows a close-up of the left hand side pictures. This is a close-up of the left side figure. So it means that the solutions, they are clearly diverging when we are using a relatively large time step size of 0.1. Now to see the effect of time step size, we reduce the time step size by an order of magnitude and repeat the calculations and try to have converged solutions. So our previous results, they corresponded to delta T equals to 0.1. Now we use a smaller time step of 0.01 and repeat our calculations. So here in the next step we perform our calculations. So again, this is the mass matrix, this is the degree of freedom vector, this is again the mass matrix, this is the degree of freedom vector at the initial condition, this is the new delta T of 0.01, this is the load vector, and then this is the delta T, this is the stiffness matrix, and this is the initial gas temperature. So we get AT equals to B at the first time level, and then we get a certain set of solution. Let us go for the next step of solution using this data as the initial guess for the second level. For n equals to 1, use this data as the initial condition. Then we are using these values here. So values of temperature obtained from n equals to 0 calculations. So we are repeating the calculations, just we are using the new value of temperature, and then we are generating the new matrix equation system A T2 equals to B, and then we are finding that the values of the degrees of freedom, they are slightly changed. Now we shall repeat the calculation for more number of time steps to see the effects of this reduced delta T. Then we find here that we have gone for third level, fourth level and fifth level. We have summarized few results, and here all the results we have combined for much longer time steps. So we have shown, plotted the results for large value of n. So at 4 different nodes, we have temperatures T2, T3, T4 and T5. So here we have shown, this is node 2, this is node 3, this is node 4, this is node 5. So these are the global nodes. So here we have shown the temperature distribution with respect to time, and we can see that the temperature is just increasing. The solutions are diverging even with delta T equals to 0.01. So we observed two cases. In the first case, we have used delta T equals to 0.1. We found that divergence was occurring very fast. Then we reduced the time step and went to 0.01, and then also we are finding that the solutions are diverging. So now we shall reduce the time step once more by another order of magnitude. So we shall use delta T as 0.001 and repeat the calculations. So here we are using delta T as 0.001 and repeat the calculations. So we have this mass matrix. This is the degree of freedom vector T1. This is again the mass matrix, that is constant. So this is the initial gas, temperature at the initial level. So this is the load vector F at all levels. So it is not changing with time. And then we have the stiffness matrix, that is also constant. And we have the temperature or degree of freedom at the 0th level. By simplification, we get the matrix equation system A T1 equals to B, and then after solution we get the first level of data. Now this solution at the first level we use for n equals to 1 calculations. So here we have shown for n equals to 1 calculations, the temperatures we are showing. We are then getting the matrix equation system here as A T2 equals to B, and then we are getting the solution here at the second level. Then we are going for further calculations with increasing time step. So at n equals to 2, n equals to 3 and n equals to 4, we are getting the solutions, and finally we are showing the results. And in this case we can see that our results have converged when we are using delta T equals to 0.001, but the solutions they are. So if we see here at around T equals to 400 seconds, the solutions appear to converge, while using delta T equals to 0.001. Therefore, we learn from this case that the explicit schemes are conditionally stable, so that the time step size used in the explicit scheme we have to find out from the stability criterion. So we have used 3 values of delta T. So delta T 0.1, delta T 0.01 and delta T equals to 0.001. This is the summary. The first 2 cases they diverged. We did not get solution. In the last case we got converged solutions. So this is the summary of results. Now we have 2 more cases, the unconditionally stable cases. The first case is the implicit scheme and the second case is the Crank-Nicolson scheme. So now we first show with the implicit scheme where we use a high value of time step of delta t equals to 0.1. The explicit scheme failed to yield converged results with delta t equals to 0.1 and 0.01. Now we use a high value of delta t for the implicit scheme and we want to see the effects of this time step size. We expect that since the implicit scheme this is conditionally stable, it will give us stable or oscillation free converged solutions. So here this is the generic form which we get for the implicit formulation. So our semi-discrete formulation was m dt plus kt equals to f. The implicit scheme, it renders m t at n plus 1 minus t at n by delta t plus stiffness matrix into temperature at n plus 1th level equals to the load vector at n plus 1th level. So m, k and f, these matrices and vectors, they remain constant with respect to time in the given problem. So here we have written the first step of calculation. For n equals to 0, we use the trivial initial solution that all the unknown temperatures are 0, and using those temperatures we find the first level of temperatures. Here this is our mass matrix that is constant, then we have delta t, then we have our global stiffness matrix. Now this is the unknown temperature vector. Then here we have again the mass matrix, we have temperature at the initial condition plus this is our delta t and this is our load vector which does not change with time. Then we have generated the AT1 equals to B matrix equation system after the simplification. From here we got the first solution at the first level. This we use for the n equals to 1 calculations. So for the next calculation, for n equals to 1, the solutions for n equals to 0 are used as initial conditions. So this is for n equals to 2. So this is our delta t, this is stiffness matrix, this is mass matrix, this is temperature at level 2, this is again the mass matrix, this is the temperature which we got at the first level after using the first set of calculation. So this is also delta t and this is the load vector. Then we generate the second level of matrix equation system, AT2 equals to B. From here we get a solution. Now we show the next steps of solutions that we obtain using the similar calculation. So for n equals to 2, n equals to 3, n equals to 4, we have summarized our results and we can see that using n equals to 9, this temperature obtained using n equals to 9, we get that we have reached the exact solution. It is approximately equal to the correct solution, this value. So here we have plotted the results obtained using the implicit method. We have used two values of time step. So delta t, this is 0.1, and second case we have considered a smaller time step. So delta t is 0.01. In both cases we can see that we have achieved oscillation-free solutions that match our exact solutions. So this shows the effectiveness of implicit method to yield oscillation-free accurate solutions using a higher value of time step. Therefore, implicit scheme performs better than explicit scheme using high delta t. And this is not a new result, this is our expectation as expected. Now we have the last method, that is an average of explicit and implicit methods. We say that this is the second order accurate Crank-Nicolson method, which is unconditionally stable. So the previous two methods, the explicit method and the implicit method, or the forward and backward Euler methods, they were first order accurate. In many cases, we use the Crank-Nicolson scheme for the parabolic type of marching problems for the second order accuracy of time. Here we have the generic equation. So this is the generic equation for Crank-Nicolson method. So we show the calculations here. So this is our global mass matrix. This delta T we are using here, high value 0.1. So this is delta T by 2. So this is our global stiffness matrix. This is our unknown load vector. So this is again the mass matrix. This is delta T. This is the global stiffness matrix. This is the initial condition. This is the delta T, and this is the load vector at any time. Now by simplification we find the matrix equation system AT1 equals to B, and from there we get the first level of solutions. This first level of solution, it is used for the next calculations. So here we have shown three solutions for n equals to 1, n equals to 1, n equals to 2, and n equals to 3. Then we found that we reached very close to the desired solutions. Now we have shown the final plots of the converged solutions obtained using Crank-Nicolson method. We have used two different values of time step. We have used delta t equals to 0.1 and delta t equals to 0.01. In both cases, we found that results converged. We have distinguished between the explicit and implicit schemes of time integration. We have demonstrated GFEM, explicit, implicit, and Crank-Nicolson solutions for a marching problem governed by parabolic PDE. The explicit scheme failed to achieve convergence with the time step size of 0.1 and 0.01, while the implicit and Crank-Nicolson schemes yielded stable solutions with both of these delta t values. In our explicit calculations, we have not used mass lumping. We have used the global consistent mass matrix. The explicit schemes, when diagonalized, lead to a matrix equation system where the algebraic equations are decoupled, leading to the one equation, one unknown situation. The implicit schemes, however, always lead to one equation, many unknowns situation. For today's class, I recommend the texts authored by Professors T.J.R. Hughes as well as J.N. Reddy. Thank you very much for attending this class.